Hello everybody, welcome to Omega Toppers Academy. My name is Kaushal and today let's have a demo class on work energy power for the class 10. This class pertains to ICSE syllabus of 10 standard and does not relate to the reduced syllabus for CBSE and state. But you guys can still learn something from this, so let's get started. We have more full length discussions coming up for class 10 on this channel. Stay tuned and like, share and subscribe. So let's start today's class. So, in our daily lives, we say that work is being done. When do we say that work is being done? Let's say I'm doing some housework. Let's say I'm sweeping the floor, mopping the floor, cleaning my room. If your mom asks me what I'm doing, if sorry, my mom asks me what I'm doing, I'll say I'm doing work. But in science, specifically physics, the word work has a very specific meaning. So, whenever I say that work is being done, it means that the body is getting displaced, under the application of a force. So work is said to be done only when the external force applied on the body produces a displacement in it. Let's say I have a wall. Let's say I have a wall and I am standing here and I'm pushing the wall. I am applying a force on the wall as much as my muscles can. But is the wall moving? No. But am I getting strained? Yes. I feel tired after pushing the wall for some time. I'm definitely spending some energy, but work is not done. Why? Because the wall does not move. There is no displacement on the wall, so that I can say that no work is done. But let's say I have a car. Let's say I have a car and I'm standing here and I'm pushing the car. So I notice that after a certain amount of force, the car starts to move in the direction of the applied force. So, whenever there is a displacement in the direction of the applied force, I can say that work is being done. Alright, so let's move on to the next concept. Let us move on to the measurement of work. How do we measure and calculate work? So, let's come to the topic of measurement of work. I told you that two things are necessary for work to be done. One is the application of force, and the other is the displacement. So I can say that work is the product of force and displacement. Okay, but these two have to be in the same direction. The displacement that is produced has to be in the direction of the force applied. So the magnitude of work done is equal to magnitude of the force applied into magnitude of the displacement that is produced. For example, if I have a block placed on the floor and I am applying a force of 10 Newton in the horizontal direction, after some time the body has moved by a distance of 20 meters. Now, to calculate how much work is being done, all I have to do is multiply the magnitudes of force and the displacement along the direction of the force. So I have 10 Newton, which is the magnitude of my force, and 20 meters, which is the magnitude of my distance. So 10 times 20 gives me 200 Newton meter. We call this Newton meter as joules. So the unit of work is joule. So 1 joule is defined as when 1 Newton of force displaces a body through 1 meter, I can say that 1 joule of work is done. But in this case, if I observe, the force was in the horizontal direction and the displacement was also in the horizontal direction. But what if that is not the case? For example, let us say I have an inclined plane, right? I have an inclined plane which is inclined at an angle of theta with respect to the horizontal. I have a block which is placed here. Okay. Let us say I'm pushing the block in this direction. This is my force applied. In which direction do we think the block will move? Is it in this direction? Will the block move horizontally? No. The block will move here in this direction. So if I see, if I notice, my force is in this direction, but the displacement is in this direction. Because after a while, the body will be here. So I can say that this is my displacement, which is D, and the force is applied in this direction. So I need to find the component of the displacement in the direction of the force, or I need to find the component of the force along the direction of the displacement. So if I draw a vector diagram for the force and displacement, my force is in this direction and the displacement is along this direction. So for now, we will ignore that the force is in this direction. So what I'll be taking is the component of displacement along the direction of the force. So for now, I'll call it as x. If I complete this triangle, I see that it's a right angle triangle. So I'll name this triangle as triangle AB and C. This will of course be a right angle. And since this angle is also theta, we just saw that this angle is also theta. In this triangle ABC, I will apply cos of theta. So cos of theta will be BC by AC, and cos of theta, BC is x and AC is the B vector. So x will be equal to d cos theta. So this d cos theta is the component of the displacement along the direction of the force. So based on the definition of work done, I have work done is equal to force into the displacement along the direction of the force. But the displacement along the direction of the force is d cos theta. So my work done is given by F d cos theta. So the symbol d that I've chosen is just arbitrary, and you can also use the symbol S for displacement. So the work done will be F S cos theta. Similarly, if I were to calculate the component of force along the direction of displacement, it would be F cos theta. Alright. So according to the definition of work done, I have work done is the force and displacement, product of force and displacement. So if I multiply this, I will still end up with F into d cos theta. So this means that I can take the component of force along the direction of displacement or the component of displacement along the direction of the force. As long as the force vectors and the displacement vectors are acting in the same direction, the work done is calculated. So this is the formula that you guys need to remember. Work done is F into S cos of theta. Now let us look at some special cases where this formula changes a little bit. So the general formula is work done is F into S cos theta. Since I have this cos of theta, this is my variable. As theta changes, the value of work done changes. As in the angle between the force and the displacement changes, my work done changes for the same magnitudes of force and displacement. So let us look at the first case when theta is equal to 0. What do I mean when I say that the theta is equal to 0? It means that the force and the displacement vectors are acting in the same direction. This is my force vector and this is my displacement vector. So if I look at it here, the angle between the two vectors is 0 degrees. So I know that cos of 0 is equal to 1. So work done will be F into S into 1. So this is F into S. So I can say that my maximum work is done when the angle between the two vectors is 0 degrees. Now, the second case is when theta is equal to 90 degrees. What do I mean when I say that theta is equal to 90 degrees? I mean that if this is my displacement vector, this is my force vector. So the angle between the two are 90 degrees. This means that the force vector and the displacement vector are perpendicular to one another. So I know that cos of 90 degrees is equal to 0. So if I substitute that in my work done formula, F into S into cos of 90. So anything multiplied by 0 is 0. So this is 0. So whenever the angle between the force vector and the displacement vector is 0, I can say that the work done is 0. Now the third case, when theta is equal to 180 degrees. What do I mean when I say that theta is equal to 180 degrees? So the angle between the force and the displacement vector is 180 degrees. That means that they are acting in the opposite directions. I know that cos of 180 degrees is equal to minus 1. So work done will be F into S into cos of 180. This is minus 1. So work done is minus F into S. Let us move on to the next case. When the body moves in a circular path. Let us say this is a circular path. Let us say you're starting to run from point A and you run all the way in this direction and you come back to the starting point. So the effective displacement that you have undergone will be equal to 0. If you finish at the same point you're starting at, the displacement is 0. Even though you've traveled some distance, the displacement that you've undergone is 0. So the work done in this case, F into S cos theta, S itself is 0. So my work done is 0. So these are the special conditions of work done. So that's all for today's video. Hope you guys learned something and had fun in today's class. The PDF of today's class is available in the description box below. This demo is just a short introduction to the kind of coaching you can expect at Omega Toppers Academy. We pride ourselves on providing individual attention to each and every student because of our limited batch sizes. We offer a hybrid mode of education, both offline and online. If you like our content, please subscribe so you don't miss out on our new videos. Thank you.